Welcome to Online Math. This is Chapter 3. Mappings, functions, and graphs. Let's begin with a simple picture of the complex plane, mapping f of z equals z squared. To realize this, an easy way to observe this is take a small portion of the complex plane. Let's make this be described from r equals 2, r equals 3, and from theta equals 0 to theta equals pi fourths. Now, we all know that a function can be written, a complex number can be written in polar form, and so it's r e to the I theta squared, which is r squared e to the I 2 theta, which tells us that now r, which used to be 2, has been brought out to 4, and 3 has been sent out to 9, so that's a bad location of 9, but we'll get 9 over there. And now the old angle theta equals 0 is still 0 because twice 0 is 0, but twice pi fourths is pi halves. And so the inside, we haven't actually been certain yet that that's still preserved, but it appears this is what's happening. Now, to simply check a single point, you can pick some point, let's say right there at 2.5 as the radius, and pi eighths, if we double it, it'll have an angle of pi fourths, which would be here, but 2.5 squared would be about there, not halfway from 4 to 9. So now we have an idea of how these maps tell us what's happening. They are not a great three-dimensional picture, but they're at least two two-dimensional pictures, and since 4 dimensions is lacking to us, so be it. All right, so now I'm going to try another map that looks like this. It's similar. This time it's going to be 1 over z. This is called the inversion map. We're going to try the same process. But of course, it's useful to think about the correct form of the complex number to use here. And again, I'm going to use that z equals r e to the I theta. And so f of z then will be 1 over r e to the I minus theta. So what that tells us is that we pick any point in the complex plane, then its image will have the reciprocal radius and the negative of the angle. So let's make this one be less than 1, so the reciprocal will be bigger than 1. And if this was theta, this being minus theta, there's the image. So it's flipping it upside down, and it's making things smaller, bigger. But at the same time, it's making things bigger, things smaller, because if an r was bigger than 1, its reciprocal would be less than 1. So I'm going to put r equals 1 as a reference. And that means over here, if I put r equals 1 as a reference again, things in the inside are being mapped outside. Well, I'm going to do this. I'm going to guess that this is what it's got to look like. And so there's what the inversion does. It inverts the outside to the inside, but guess what? It also takes the outside and moves it to the inside. And of course the angle flips. Now it does two things. It flips the angle and inverts the radius. So what's really interesting is two inversions are taking place, both the radius and the angle. Which means that this might still be conformal. What used to be measured from here to there might be measured that down, but maybe the location is it still will be measured as a positive angle if that one's positive and negative if that one's negative. So it's very clear that the question of conformality may be investigated in these pictures, and I think we know that the function 1 over z, or z to the minus 1 has a derivative, so we expect this to occur. Now, we left off at having looked at some very specific functions called the Möbius functions, and yes, I pronounce it strangely. Little side note, there's an old-fashioned picture novel done by Möbius. All right, now the Möbius functions look like this. F of z equals az plus b over cz plus d, and we want to make sure that ad minus bc is not 0. Now, if we had lived in the real world back in the day, where we had the real cross the real, why, we would know what these functions would look like. Don't treat z as a complex, treat it as a real number. Well, first thing is, x equals, minus d over c would be a bad number, so we're going to have a vertical asymptote, and as x would go to infinity, we would get y equals a over c as a horizontal asymptote, and it's pretty clear that we're used to graphing these types of things. And in reality, a over c never comes out of this function, and minus d over c is never allowed to put into it. So just for the time being, I want you to realize that if I have a whole set of complex numbers that have this property, that they're getting very, very large, say going to infinity, why don't we treat the entire outside of the complex plane, way out here, is z equal infinity. All the infinities are the same. Let's treat it that way. So there's the complex plane with an additional point. So some people call that C star, other people call it Z closure, others people call it the CP, or the 1-point projection of the complex plane. So be it. For the time being, I just want to treat infinity as a single point. It's way out there in any direction. Now, if we have f of z equals az plus b over cz plus d, and ad minus bc is not 0, why don't we just observe that certain things are easy to do, like evaluating this? And when we evaluate it, we see certain things happen. So I want to summarize something about this. I want to summarize that, first off, this is true all the time here, but let's do this for z not equal to minus d over c. Now, if z equals d over c, do you think that it's reasonable to call this infinity? So I'm going to do a calculation off on this side. I'm going to write it a plus b over z plus c plus d over z, and I'm going to set z equal to its polar form, a plus b over r e to the minus I theta over c plus d over r e to the minus I theta. I just changed r to z to r e to the I theta and then put everything where they belong. Now I want you to notice, as if we let, in this form, r go to infinity. Oops, I was looking at the wrong point. R going to infinity. Well, this will go to 0. This will go to 0. And if we're going to infinity along a fixed angle theta, this will basically be held constant, but it doesn't matter. Its value is always on the unit circle. 0 times a norm on the unit circle is going to be a very, very small normed value. This goes to 0. This goes to 0. So we're going to get a over c as z goes to infinity. So it seems that we can say z going to infinity, we can say that we get a over c, just like what we got in the real plane. Now, are we going to get infinity out when c goes to a constant value d over z? And I leave it for you guys to do the same type of limit, but as z goes to minus d over c, it says it's very reasonable to say that this is infinite. That is, the norm of z has gone to infinity. It seems that three things describe this function. There are certain values that can be evaluated, certain values that come out when you put in large values, and certain infinite values come out when you put in small values. Well, let's write one of those down and demonstrate how this can describe a function. So let's write down f of z equals z minus 1 over iz plus I, which can also be written as z minus 1 over I times z plus 1. Now I want you to know that f obviously changes 0 immediately into, well, 0 minus 1 over I. Is that right? So 0 minus 1 over I, which multiply the top bottom by I, we get I. Now I could have also evaluated it at 1. Plug in 1 and I'd immediately get 0 in the top. That's very nice. I can keep doing this. It turns out that I want to make use of these facts. I want to plug in A over C. So in this case, I'm going to plug in the minus 1 and observe that I'm going to say that I get infinity out. And then I want to say that I can plug in infinity. Is that what I want? Infinity. And then I'll get out, well, that I want the A over C, so I want the 1 over I, which is minus I. There's lots of ways that this can be described. Well, how many do we need to describe this function in its entirety? I've listed 4. I could list several more. For example, we could plug in I, right? And what would we get then if we plug in I? We'd get I minus 1 over I minus 1. Why, we'd get 1. It seems that there's an infinite number of values available, but since the function is known to be Möbius and known to have only 4 possible coefficients, let's see what happens if we can specify the fewest amount possible. So let's try this again. And let's specify simply that we know 1 is mapped to 0. Let's specify that minus 1 is mapped to infinity, well, modulus at infinity, if we call that a point. And let's also specify I gets mapped to 1. And let's not specify anything more. But now let's throw away this function and just say f is Möbius. Well, do you think these 3 values are enough to completely recover the function f? Does this just... So let's begin with f of z is a Möbius function. And we're going to let 1 by f be matched to 0. So that means f of 1, which is a plus b over c plus d is equal to 0, which c is going to be b is going to be equal to minus a. Next, we want minus 1 by f to be mapped to an infinitely large value, so f of minus 1, which is equal to a times minus 1, b is minus a, all over c times minus 1 plus d. Well, that's because we want the bottom to be equal to 0, so we have d equal to c. And so now the last step is we want I to get mapped to 1. And so f of I is going to be an a times I plus b is minus a over, and then c times I plus c. And so this is going to be a times I minus 1 over c times I plus 1, multiply top and bottom by 1 minus I. And when we do that, we're going to get a minus a and minus 2i when we multiply it out and cancel the 1s. And then the bottom is going to be 2c. And so this we want equal to 1, so we have 2ai over 2c equals 1, which is c equals ai. And now when we plug that in, we find to get f of z equals a z minus a over c. C is ai. A-I-Z, and what's D is C? D is C plus AI, which will be A times Z minus 1 over A-I Z plus 1, Z minus 1 over I Z plus 1, which is exactly the function that we began with, that we claimed that these values are mapped to, but we only made the assumption that it was a Möbius function. The three problems, which we attach to the PDF that you get to do. First is if f of z is equal to az plus b over cz plus d, that f inverse exists when AD minus BC is not 0. Second, we're going to define a very strange symbol, z, comma, z1, z2, z3, as being equal to, and this is called the cross product notation. So we're going to do this as z minus z1 times z2 minus z3 over z minus z3 times z2 minus z1. And if we call this our function f of z, it's clearly a Möbius function, since this is constant, that's constant, and we have a Möbius function. Now, the strange thing about this Möbius function is it's very clear that when you put in z1, you're going to get 0 over a value. That when you put in z2, you're going to get z2 minus z1, z2 minus z3, z2 minus z3, and z2 minus z1, you're going to get 1. And last but not least, if you put in z3, we're going to get infinity. So this term here, called the cross product, is a very special function. z1 under the cross product gets mapped to 0, z2 gets mapped to 1, and z3 gets mapped to infinity. So this is a very specific Möbius function that has these properties. Your homework is to show that if g is any Möbius function, then if we have 0, z1 mapped to 0 by g, z2 mapped to 1 by g, and z3 maps to infinity by g, then g is identically the same as our cross product term. Now, the easiest way to show this is to simply observe that this is the best method, I think. F inverse exists, and then calculate G composed with F inverse. Third step for your Möbius function is I simply would like you to find a Möbius function that sends I to minus I, 1 to 0, and let's take infinity to 3. Going to be nasty.